eSig, and I want to welcome you to our monthly webinar series and give you a little bit of background on eSig. For those of you not familiar with eSig, we're a membership-based nonprofit organization that provides our members with objective information, resources, networking opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and we produce technical resource materials. eSig also serves in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. eSig leads one of the 5 pillars, which deals with the research agenda for the system operators. And more information on GPST can be found at www.globalpst.org. At eSig, we recently completed a virtual workshop on generator interconnection, which you can still view on our YouTube channel. And now we're preparing for our fall technical workshop, which starts October 24th in person in Minneapolis. Our workshops, our monthly webinars are open to everyone. Please feel free to register on the eSig website. If you're new to eSig, I strongly encourage you to follow up with us. If you like what you hear, I think you'll be pleasantly surprised. You can find us on the web at www.esig.energy, as well as LinkedIn, Facebook, and Twitter. Okay, so just a few logistical matters before we get started. Everyone's lines are going to be muted for the duration of the webinar to avoid unnecessary distractions. And for questions and answers, we're not going to be using the WebEx platform. We've moved to the Slido platform. So we're asking you to go to slido.com, enter in ESIG6, ESIG6 as the event code. And it's also listed here on this front slide. There's a thumbs up button next to the questions, so you can cast a vote to help prioritize which questions get asked first. We plan to save 10 to 15 minutes for questions and answers at the end. We'll wrap it up at the top of the hour, and an email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through the slido.com platform. So today's topic is resource adequacy with a new toolkit that has been developed. Resource adequacy is, of course, a really hot topic these days, coming off of resource adequacy events in CAISO in 2020 and in ERCOT in 2021. Most recently, the very close call we had in CAISO in early September with the multi-day heat storm. And that resulted in a new peak demand record, but luckily no shortfalls. eSig has a resource adequacy task force. We've been making recommendations to improving resource adequacy modeling and metrics. Now it's turned to looking at capacity accreditation, and you can download the report that the task force put together on rethinking resource adequacy from our website. And in line with a lot of these recommendations, GridLab has been supporting development of a new resource adequacy tool, the GridPathRA Toolkit. This was launched in September. And today, Dr. Elaine Hart and Dr. Mileva are going to be presenting the toolkit along with a case study examining resource adequacy in the Western United States. So Elaine is the founding principal at Moment Energy Insights, LLC. And previous to that, she was at Portland General Electric and resource planning, and also at E3. And Anna is the founder of Blue Marble Analytics, which developed the software platform, and also was previously at E3. So just a short reminder again, use slido.com with the event code of ESIG6 to ask questions. Okay, without any further ado, let's go ahead and get started. I'm now going to turn it over to Elaine, who's going to give the presentation.
So much, Debbie. Can you hear me okay?
Yes, we can hear you fine.
Excellent. Thanks so much. Good afternoon, everyone. Before we get started, we want to thank eSig for the opportunity to present today and GridLab for sponsoring this work. We also want to thank Michael Milligan and Justin Sharp for providing technical review, guidance, and some tough questions throughout this effort. As Debbie said, my name is Elaine Hart. I'll be presenting on behalf of our team today, but I'm joined by Mileva as well from Blue Marble Analytics, and she'll be available as well to answer questions at the end of the presentation. I think by now the motivation for this work is probably clear to most of you listening in today, but just to set the stage a little bit, we started thinking up this project in the summer of 2020 when the West saw its first major load curtailment since the energy crisis. We'd spent our careers so far working to develop planning tools for cleaner energy systems, and resource adequacy had already become a critical aspect of that work. And despite the prominence of resource adequacy in the headlines during that time, and a lot of great work going on into cutting-edge RA analysis for individual systems across the West, what we couldn't find was a holistic evaluation of RA risk across the entire region, and an analysis that addressed new risks and opportunities presented by clean energy technologies, and that accounted for the significant interdependencies that we experience across the Western grid. So we set out to develop a public tool and a public data set to help do just that. And that's what we're presenting today. The GridPathRA Toolkit is an open source tool for conducting RA analysis in the Western United States. It leverages GridPath, which is an open source power system platform developed by Blue Marble Analytics. You can find GridPath on GitHub at the link here on the slide. GridPath can be used for all sorts of analyses, including capacity expansion and production cost modeling. The way we use it for RA in this study is pretty limited. We've stripped out a lot of the functionality, we've thrown out economics, and we effectively just minimize unserved energy given all the physical capabilities and constraints on the system. But future analyses could be more sophisticated. You could incorporate economics and a lot of other features that GridPath offers. And because it's open source, users can actually develop their own features as well if they really want to dig in. The toolkit also includes some accompanying code that develops and post-processes RA runs in GridPath. There's a separate link for that here on the slide. And if you follow that link, you can also find a toy example if you want to get started and learn how to run these cases yourself. And finally, the toolkit includes the data set that we developed for the study that we're going to present today. It's all based on publicly available data, and we're making it available to you in hopes that it helps support important work in RA and electricity sector analysis across the West. So with the motivation that I described at the outset of the presentation, we focused our work on 3 key features that we thought would be important for RA analysis in the West going forward. First, weather correlations, and specifically correlations over very large geographical areas that are larger than the scale of some weather systems. We offer 2 different approaches to this, Monte Carlo simulation and weather synchronized simulation, and we'll get into those in more depth later in the presentation. With respect to energy limited resources like hydropower and energy storage, we're interested in recognizing both the opportunities provided by these resources and the unique challenges that they pose. GridPath optimally dispatches these resources, including hybrid renewable plus storage projects, subject to all of their operating constraints so that we can minimize lost load. And finally, transmission and regional coordination are important, not only as we think about regional RA programs and expanding markets in the West, but also just in recognition of the interdependencies on the system that we experience today. Our study uses a zonal transmission topology, and we'll demonstrate one approach to accounting for regional interactions when analyzing RA for an individual system. To demonstrate the capabilities of the toolkit, we conducted a case study of the Western US. We used Monte Carlo simulation to explore 3 different scenarios for the year 2026, and those are listed here on the slide. They include a no additions scenario, which incorporates all planned retirements, but no planned additions through 2026. A California additions scenario, which incorporates additional resources in California to broadly align with the CPUC preferred system plan. And a less coal scenario, which incorporates those same additions in California, but also retires an additional 11 gigawatts of coal elsewhere in the West. For each of these scenarios, we also conducted some sub-regional analysis, where we zoomed in on parts of the system that were inspired by the CAISO and RAP RA programs. For these sub-regional analyses, we took a look at RA risks if each system was treated as an island, and we compared that to the RA risks if the system was able to leverage imports from the rest of the West. We'll talk about this more, but it was really important that our import cases recognized not just transmission constraints, but also reflected coherent weather conditions across the West. So in periods where weather is affecting the availability of excess generation across the West, the model recognizes that and limits what can be accomplished through imports. Comparing these cases highlights how sensitive RA analysis can be to import assumptions and flags this as a key area of focus for resource planners. And finally, at the bottom here, we'll discuss weather synchronized simulation, an alternative to Monte Carlo, and we'll highlight some key learnings and opportunities for future analysis on that front. I won't go into all the details here on methodology. Happy to answer your questions on that at the end. But before we jump into the findings, I do want to give you just sort of a high-level sense of our approach. The first step in our analysis is to determine a wide range of potential conditions that the system could encounter across different weather conditions, hydro conditions, and combinations of forced outages. Then we test the ability of the system to meet load and contingency obligations across all of those conditions using GridPath. Now, you can see on the right here, where we've shown the data availability across some of the key variables in the model, that publicly available high-resolution data that we need for RA analysis is limited across the historical record. And so that means that the number of conditions that we can test in these types of studies is also limited. Monte Carlo simulation provides a way of synthesizing plausible conditions from these data sets by mixing and matching load, wind, and solar from similar historical weather days. This allows us to generate many more sets of conditions than were actually experienced in the historical record, and that allows us to estimate RA metrics with high precision. Unfortunately, that precision does not guarantee accuracy. And we go into this in more detail in the report, but Monte Carlo analysis in this application tends to suppress some of the important correlations during the most extreme events. That said, this approach has been adopted by many planners sort of out of necessity, so we're leveraging it here. And in the report, we talk about some of the ways that we try to minimize this particular issue using sort of intelligent binning strategies around weather. We also pose weather synchronized simulation as a possible alternative to improve the treatment of key weather correlations, but we'll get into that a little bit later. All right, so let's jump into our scenarios. The first scenario we'll look at is the no additions scenario. Recall, this incorporates planned retirements, but no planned resource additions through 2026. So we expect it to be short, and we expect to find some RA challenges in this scenario. Here you can just see the makeup of the resource fleet across the West graph here. Sure enough, we did find some RA challenges in this scenario. Now, there are a lot of ways to quantify RA risk. For each scenario, we've provided some of the same information in the same format here, so you can sort of compare between them. On the right, upper right here is a table with some of the key RA metrics that we include in the report. In the report, we go through definitions of all of these, and we present them for the sake of sort of comparison across different types of metrics and for the sake of transparency. But just for the conversation today, the metric that I'd like to focus on is the loss of load expectation, or the LOLE. That's the second number here in the table. This is the number of days every 10 years that we would expect the system to encounter lost load based on the simulation. Many systems are planned to a 1 day in 10-year loss of load expectation standard. And you can see that the no additions scenario has an LOLE of 18 days every 10 years, so it does not meet the 1 day in 10-year standard. This is a resource inadequate system if you use that particular standard. We don't advocate for use of that particular standard. There are a lot of issues with the 1 day in 10-year standard, and there's a lot of good work going into rethinking RA metrics and RA standards, much of which is coming out of ESIG. But for the purposes of comparing scenarios in a transparent way and grounding this work in metrics that people are generally pretty familiar with, we do rely on the 1 day in 10-year standard throughout the report and in our discussion today in this presentation. In addition to those metrics, we also show for each scenario the distribution of loss of load hours by month and hour ending. That's the heat map on the left here. And to the right of it, you can see a distribution of loss of load events in terms of their duration. We find for this system that without taking action, it has shortages in the evening on very hot summer days, and the loss of load risk is highest in August during hour ending 18. And all of this is in Pacific Standard Time. The good news is that the events are pretty short in duration. Most are 4 hours or less, and no shortages longer than 8 hours were observed for this case. We also present RA risk in a couple of different ways in the report, one of which we want to walk through here. This is a heat map that helps you understand not just the size of the shortage in terms of capacity, but also energy. In this heat map, every cell represents the event size in terms of the capacity shortage across the top and the energy shortage down the side here, experienced during the event. The number and color corresponding to each cell represent how often that size of shortage was observed in the simulation. So these heat maps can be useful for thinking about potential solutions, as we'll show over the next couple slides. In the first example here, we add 10 gigawatts of perfect capacity to this system. That means that there's an additional 10 gigawatts of capacity that's always available in all hours. And that allows us to avoid all of the events to the left of this vertical line here. It also reduces the magnitude of the events that fall to the right of the line. For this system, that 10 gigawatts of perfect capacity would get us to a 1-day and 10-year standard. It would actually be a little bit below the 1-day and 10-year standard. But it begs the question, do we really need 10 gigawatts of perfect capacity that's available all the time to meet the 1-day and 10-year standard? There's not a lot of long duration events. Those would show up in sort of the bottom left portion of this graph. And so we probably don't need perfect capacity. In this next example, we provide a little more capacity, 11 gigawatts, but it's not perfect. It can only provide 26 gigawatt hours to the system when it's dispatched. So this resource has a duration of about 2.4 hours. And so we're only able to eliminate the events in the shaded rectangle. But we're still able to achieve a 1-day and 10-year standard by adding this resource. It turns out you can draw a whole bunch of these rectangles that achieve the same RA standard for any given system. And when you consider all of them together, you can find an efficient frontier of potential solutions. And that's what we show here. This curve shows that if we hypothetically had perfect capacity, we would need 9.3 gigawatts of it to achieve the 1-day and 10-year standard. If we only had enough energy to run that capacity for 4 hours each day, we'd still only need 9.3 gigawatts of it. And in fact, the curve doesn't really start to pick up until the duration falls below 3 hours. If you have only enough energy to run your capacity for 2 hours each day, then you need a few more gigawatts of that capacity to achieve the same RA standard. There's a cost minimizing point along this curve. That will depend on the relative costs of the solutions with different durations. But even without cost information, we can look at this curve and see where it sort of bends and see pretty clearly that the cost optimal point for this system is probably not longer than 3 or 4 hours of duration. There's not a lot of benefit to adding duration beyond 3 hours. So this all suggests that this system is a great fit for energy storage and flexible load programs. Now I'd like to briefly touch on the sub-regional analysis for this scenario. As a reminder, in the sub-regional analysis, we zoom in on 2 footprints, which were inspired by the CAISO and RAP-RA programs. I say inspired here because this is a physical model of the West. We don't track loads and resources by load serving entity or by contractual obligations in the study. I will say that if that data was readily available, it could be layered onto this analysis to yield additional insights, but we did not undertake that in this first study. For now, we're sort of demonstrating this sub-regional analysis as a proof of concept just using the physical model. So we approximate the CAISO and RAP subareas by assigning loads and resources by BAA according to the table you see here on the slide. So all the typical sort of caveats apply. You cannot actually infer RA positions for either program from the analysis that we're about to see, but I think they're interesting insights nonetheless. As I mentioned earlier, we test these subareas as islanded systems and as systems that can import from the rest of the West, subject to transmission and resource availability constraints under coherent weather conditions. In the import cases, unserved energy is only logged if it's experienced in both the islanded simulation and the west-wide simulation. If unserved energy is experienced in the west-wide simulation but not in the islanded simulation, then we can infer that that unserved energy is due to a shortage somewhere else outside of the system of interest. If instead the unserved energy is experienced in the islanded simulation but not in the west-wide simulation, then we know that there's enough excess generation available somewhere in the West to help the system of interest avoid lost load. So this approach really focuses on those events where the system of interest is constrained at the same time that the rest of the West is constrained. These are the really challenging situations from an RA perspective. For the no addition scenario, I'm just going to talk about the results from the CAISO subarea analysis because it's the more interesting one. Without imports, as you probably expect, the system had much higher loss of load risk. Shortages were observed over more months of the year and more hours of the day. You can see this on the heat map on the left. Perfect capacity needs for the CAISO subarea were about 11 gigawatts when it was treated as an island. When we accounted for imports, the loss of load risk was actually pretty similar to the west-wide results. As you can see here on the heat map on the right, it looks a lot like the west-wide heat map. And imports reduced the capacity need by about 3 gigawatts. You might have expected this difference to be larger, given the significant import capability that California has. But recall that these imports are based on coherent weather conditions. So they may be severely limited when extreme weather is also affecting areas outside of California. If we jump straight to the efficient frontiers for solutions in these two cases, we see that the islanded case has some pretty substantial capacity needs, especially when the available solutions are very limited in duration, 3 hours or less. But that these needs are largely mitigated by accounting for imports. In other words, failing to account for imports makes it appear as if RA challenges are greater and longer in duration than they may actually be. And this is true even when imports are limited based on coherent weather conditions outside of the state. In this way, regional coordination serves as sort of a low-hanging fruit solution for addressing apparent long-duration RA challenges. So based on this analysis, to all the resource planners out there, I'd suggest that before you build your way out of an apparent long-duration RA challenge, you should critically examine your import assumptions. If your RA analysis limits imports in all hours based on limitations that you might only see during the most extreme events, you're probably overinflating the size and duration of your RA challenge. On the other hand, if your import assumptions reflect typical weather outside of your footprint, you might be overestimating your ability to rely on those imports when the system is really constrained and you could be understating your RA challenges. Ideally, planners will explicitly consider their own RA challenges in the context of the broader system, as we attempt to do in this study. All right, the next scenario we looked at was the California addition scenario. I'm not going to dwell on this one because it wasn't very interesting. We added the additions from the CPUC preferred system plan roughly through 2026. And what we found was that those additions eliminated almost all of the observed shortages, and the loss of load risk across the whole West was well below all of the RA standards that we tested. This is the good news. It appears that if utilities execute on their current plans, this doesn't even include the plans of utilities outside of California, that the West could be physically resource adequate in 2026. I will note that that doesn't mean we couldn't still experience challenging operational circumstances similar to 2020. There are some things that our study does not capture that come into play in real operations, including forecast errors, scheduling errors, and operational friction. Some of these could be addressed if we layered on some of the additional functionality that GridPath offers, but we didn't bite that off in this study. We assume that all resources are committed if they aren't on an outage, that maintenance is scheduled to avoid exacerbating RA challenges, and that electrons flow if they're needed. But avoiding load shed requires not just physical resource adequacy, which is the focus of this type of study, but also some operational innovation to make sure that we can leverage resources when they're most needed in an increasingly complex landscape. So let's get a more interesting scenario from a physical resource adequacy perspective. Here we see the less coal scenario. In this one, we add all of those same resources in California, but we also retire an additional 11 gigawatts of coal elsewhere in the West. This actually leaves no coal remaining in our RAP footprint. The only coal remaining here is in the Rocky Mountain area. We do find that this system is short, but it's not that short. The 1 day and 10-year standard could be achieved by adding another 3.8 gigawatts to this system. And the vast majority of shortages are only 1 or 2 hours in duration. So despite the retirement of 11 gigawatts of long duration resources, short duration solutions like batteries and flexible loads are still well suited to meeting remaining needs. I'll just leave this up for a second if you want to scan some of those metrics. So we wanted to show you an example of sort of why the system is performs so well. You can get a sense by looking at an example day. These graphs show the aggregated resource availability to serve load and to provide contingency reserves on the same day. And on the left panel, you see how that day evolved in the no addition scenario. And on the right, you can see the same day for the less coal scenario. And you can see that little tiny slice of coal left at near the bottom of the stack on the right. But you can also see the additional solar in yellow and storage in green that's available on this particular day at the top. And on this day, that additional solar and storage eliminated the unserved energy that we saw in the no addition scenario, despite the reduced availability of coal. So let's zoom into our RAP sub-area analysis for this case, because it's a pretty interesting one. Recall that the RAP sub-area has no coal remaining in this case. And so when it's treated as an island, it's pretty short. We see shortages in 10 months of the year, and we see long duration shortages in both the summer and the winter. However, if you account for imports, the winter problem goes away entirely due to the availability of excess generation elsewhere in the West, and the summer challenge is significantly diminished. In this case, accounting for weather coherent imports, reduced capacity needs, by about 6 gigawatts. And importantly, the nature of those needs, both in terms of their timing and the duration, was highly sensitive to that import assumption. So if you were to procure to solve the problem on the left, you would go after different types of resources than you would if you were trying to solve the problem on the right. When we look at the efficient frontiers for RAP, we see the same story that we saw for CAISO earlier, except it's even more exaggerated. Adopting an island assumption for the RAP subarea creates this perception that the system is energy limited and that long duration solutions are needed to ensure RA. In reality, though, this system doesn't physically need long duration solutions. It needs to be able to leverage the excess generation available from other parts of the West, namely California. This doesn't mean that this finding here doesn't mean that we will never need long duration RA solutions. If we start retiring significant amounts of fossil fuel resources and electrifying new end uses to decarbonize our energy system, we will encounter long duration RA challenges eventually. What we're hoping to do with this study and with this way of presenting the data is to show how planners can identify when they might hit that point. These types of curves will become especially useful under those planning scenarios that really stress the system, where this point where the curve starts to really rise gets pushed out to the right, and you start to really need longer duration solutions, even though we're not seeing that yet in 2026. So to summarize our findings across the scenarios, we found that if the utilities take no action between now and 2026, the West is expected to be short, but that those shortages are generally pretty short in duration and they're limited to summer evenings. We found that if California utilities execute on current plans, that the system should be physically adequate in 2026. And we found that retiring an additional 11 gigawatts of coal does create some shortages, but it doesn't pose an insurmountable RA challenge for the Western US if utilities execute on current plans. When we zoomed into specific parts of the West, we found that resource needs are highly sensitive to import assumptions, and we demonstrated one approach for planners to incorporate transmission-constrained and weather-coherent import assumptions into their analyses. We found that accounting for imports not only reduced capacity needs, but it also changed the nature of the observed RA challenge, and it shortened the duration of solutions that were needed. All right, now in the back half of the presentation, we're going to switch gears a little bit and take a look at a different modeling approach. In weather synchronized simulation, we only simulate conditions for which we have coherent weather-based high-resolution data across all the key variables. So this is different from Monte Carlo, where we're mixing and matching across these different data sets. All the simulated days reflect actual physical historical days rather than mixing and matching. This approach provides for more transparency into the physical weather conditions that drive RA risk, and it opens up some opportunities for interesting weather-based statistical analysis, which we'll discuss in a few slides. The key limitation of this approach is data availability. With weather synchronized simulation, we're really limited by the availability of wind data in particular. Our study uses NREL's Wind Toolkit, which has data from 2007 to 2014. So to demonstrate this approach, which we synthesized wind data for the years 2015 through 2020 using some historically measured hourly wind generation in VPA and CAISO and a date matching algorithm. This allowed us to probe a much longer weather record and in particular to look at some of the really challenging conditions that we've faced in recent years. But ideally, we would have actual simulated wind data for those years instead of relying on our synthesized shapes. When we applied weather synchronized simulation to the no addition scenario, we had pretty similar high-level findings to the Monte Carlo analysis. You can see the heat maps here, weather synchronized on the left, Monte Carlo on the right. Loss of load risk was generally identified in the same months and times of day, and it was just a little bit more concentrated into specific periods in the weather synchronized simulation than in the Monte Carlo simulation. This is generally what we'd expect, that the Monte Carlo simulation would smooth out some of the risk because it is mixing and matching days, and that slightly dilutes the severity of the worst days. We did not find that Monte Carlo simulation revealed important sort of potential weather situations that weren't already reflected in the historical record. This is one of the reasons that Monte Carlo simulation has been used for this purpose, to find combinations of load, wind, and solar that are plausible and challenging but may not have been experienced in that historical record. I'll say just because we didn't find this in our particular study, that doesn't mean it couldn't happen for another system, or if we were looking at different years of data. This finding for our study is probably because so many of the most challenging weather conditions for this particular system are due to heat events, and a lot of those heat events occurred in that recent weather record where we have that synthesized data. Capacity needs were also pretty similar at a high level. When we included the years with synthesized data, the system needed 11 gigawatts to achieve a loss load expectation of 1 day in 10 years. This is compared to 9.3 gigawatts from the Monte Carlo analysis. We dig into this a bit more in the report, and we attribute that 2 gigawatt difference to a slight overestimation of resource availability during the most challenging days in the Monte Carlo simulation. That comported with our expectations because we know Monte Carlo analysis misses some correlations, especially during extreme events. And in our view, 2 gigawatts is actually not that big of a difference for a system of this size. And so this finding actually sort of lends some weight to the Monte Carlo approach for this particular system. To test the sensitivity of the approach to the specific weather years being modeled, though, we did do another test where we excluded results that corresponded to the years 2015 through 2020. Those were the years where we had synthesized the wind data. So we're really limiting it to that 7-year period where we have data from NREL, and we're missing a lot of the recent weather events. In this test, capacity needs dropped to 6 gigawatts. And that wasn't particularly surprising because we were missing those recent years with the high temperature events. But this comparison highlights the sensitivity of weather synchronized simulation to the specific years for which high resolution data is available. And it really highlights the need for expanded public data sets, especially public wind data sets, to support RA analysis of more highly renewable systems. Another benefit of weather synchronized simulation is that it allows us to dig into the specific weather phenomena that drive RA risk and those that don't drive RA risk, and some of those may be surprising. Here we show weather conditions across the West in August 2020. Obviously, this was a period that did have a lot of RA risk. Those 2 days in the middle here were in the middle of the heat event. They had an LOLP, a simulated LOLP in our model of 100%. In the 2026 no addition scenario, and that was due to the extreme heat that we saw across the entire West. The day on the left here was the day before that event started, and the day on the right was a day after it ended. Across the top here, this is temperature. We've got average cloud cover in the middle and average wind speed on the right. And kind of the interesting thing you see here, which a lot of people have said a lot of times, is that when we're in the really challenging heat events, which you see in those middle 2 days, not only is it really hot, which just sends load through the roof, but wind resource is also significantly diminished during those periods. And so you can see that play out here. So these 2 days here were exceptionally challenging due to widespread heat. Here are some examples of days that were not challenging in the model, but still had significant heat at major load centers in the West. So the day on the left here, this was June 12th, 2019. It was unseasonably hot in the Northwest in Phoenix, but it was pretty mild along the California coast. The day in the middle, July 16th, 2018, was also very hot in the Northwest and east of the Cascades and the Sierras, but it was even cooler along the California coast. And the day on the right, July 13th, 2020, was even hot by Phoenix standards, but it was cool elsewhere, including the Northwest. So each of these loads might have led to very high, or each of these days might have led to very high loads and RA concerns for an individual utility where they were experiencing the heat event. But the simulation identified no West-wide RA risk on these days. The LOLP was 0, and that's entirely due to load diversity. For this particular system, high temperatures at individual major load centers seems to be a necessary but not a sufficient condition for encountering lost load. To encounter lost load or any reasonable likelihood of lost load, it has to be covering a large number of load centers, especially those along the California coast. We can take this line of exploration one step further and systematically evaluate the drivers of RA risk on the system using statistical analysis. And that's what we're showing you an example of here on this slide. We're going to walk through what can be learned from this type of analysis over the next couple of slides. We developed a simple logistic regression model that estimates loss of load probability based on that simulation as a function of daily weather variables at key locations across the West, and a couple of other variables to help the model account for hydro conditions, the time of year, and to differentiate between weekdays and weekends. I'll state as a disclaimer here up front for people interested in this type of analysis that there are very few weather days with material loss of load risk. And that means that it's really easy to accidentally overfit statistical models to this data. We took a number of steps to avoid that, and those are described in the report. I'd love to encourage the data scientists out there to build more sophisticated models for this application, but I guess I would just flag that those types of exercises should be undertaken with a lot of care and scrutiny to avoid overfitting. So our simple logistic regression model results in a set of coefficients that tell us how important different factors are in estimating loss of load probability. We find that by far weather is the most important driver, and that high temperature conditions in particular drive loss of load risk. That's not rocket science. We all kind of know that to be true. I'll note that that finding is specific to this system, and I would expect systems with much larger renewable penetrations to have more complex drivers of risk and require more complex statistical models to sort of suss out these types of insights. Now, the nice thing about this model, even though it's pretty simple, is that we have daily weather data for many more years than we have the type of high resolution data that we need for detailed RA simulation. So we can use this statistical model to estimate RA risk during conditions that we could not directly simulate due to limited data availability. Here's an example. On this slide, we took a look at the historic heat dome event in June of 2021. This event broke all-time heat records in Seattle and Portland, but you can also see on the map here that it was quite a bit more mild elsewhere in the West. As a result, the estimated LLP on this day using the statistical model was only 1.2%. And that's sort of consistent with our the insights we had when we took a look at the weather events that did result in a lot of loss of load risk, and it did not from our original simulation. We use this same approach to estimate LOLP based on weather going all the way back to the 1940s, because we have weather data for a lot more years, because we're only looking at daily weather variables instead of that really high resolution weather data. You can see that the annual LOLE in the graph, you can see the annual LOLE in the graph on the left. The turquoise line shows the results of the weather synchronized simulation, and the dark gray line shows the estimated LOLE using our simple logistic regression model. I think the interesting finding here is that you can see very clearly that the types of weather conditions that drive loss of load risk in this particular system have become more frequent in recent years. Prior to the 1990s, these types of weather events were actually pretty rare, and now we see them with some amount of regularity. This trend suggests that the findings of an RA analysis will be sensitive to the length of the historical record that's considered in that analysis. So for systems like this, which are driven by these high temperature events, including more historical years in the analysis will tend to suppress the observed loss of load risk. And you can see that on the right. In these bars, this is the total LOLE using that dark gray line on the left there, if we were to average across different durations of the historical record. And if you model only very recent years in a system like this, you'll tend to observe higher loss of load risk because those more recent years have had so many of these types of events. So we note that, without information about future weather, the decision to estimate future risk based on some number of historical years in an RA analysis, it's effectively a policy decision. A more risk-averse planner might choose to use a more recent historical record, and a more maybe cost-sensitive planner might want to look at a longer record. But it's sort of a subjective call unless we do some analysis into future weather risks. We also dig a bit in the report into the practice of detrending weather for RA applications. Some folks are starting to do this now because of these types of weather trends. We found that that approach can result in more stable estimates of RA metrics, but we're concerned that it further abstracts away from the physical conditions that are driving the risk, and we note that it doesn't necessarily provide an indication of future weather distributions. And one thing we haven't done, but seems like a natural step for this analysis, is to estimate LOLE based on future simulated weather under climate scenarios. The benefit of this statistical approach is that future RA risk can be estimated for climate scenarios without needing to generate all that high resolution data that we need for our simulation. Instead, you just need some daily weather variables at a handful of specific sites, and you can use the statistical model to tell you what the risk might be on those days. So overall, we see weather synchronized simulation as a promising area of future exploration. Compared to Monte Carlo, it offers greater transparency into the influence of weather and the potential impacts of weather trends on RA risk. However, findings may be sensitive to the years for which data is available, and the limited availability of wind data in particular in recent years poses a pretty specific challenge for this type of approach. Before I wrap up here, I just want to make one final pitch for folks to go take a look at the toolkit. Our intention in putting this together and making it public is to advance the state of resource adequacy modeling in large, highly interconnected systems like the West. This first study offers a lot of insights, but we hope that the toolkit can be used more broadly by regulators, utilities, researchers, and other stakeholders to conduct their own independent analyses and to delve into other important and emerging questions related to RA. And with that, we'd like to thank you for joining us today. We'd be happy to take some questions. And I will say we've got the link here. The report's not up yet, but it will be up soon. So we invite you to check that out in the coming days. I think there will probably be a note sent around when the report's available. Thank you, everyone.
Thank you so much, Elaine. That was a really great presentation. It sounds like a wonderful tool, and it's nice that you've populated it with the data and the model of the Western interconnections so that others can use this, and really superb analysis on the weather front as well, and sort of the drivers of resource adequacy events and some lessons learned. There's a lot of questions in the Slido, and I wanted to remind participants, if you do have a question, please don't enter it into WebEx. Go to slido.com and enter in ESIG6 and type in your question or vote questions up in slido.com. So for Anna and Elaine, there's a lot of questions. I guess I'm going to start here at the top. Mark O'Malley asks, on a recent EPRI call, it was observed that most events are not caused by lack of installed megawatts, but how they're operated. And yeah, should we be focusing on that? Elaine, you did mention this, but maybe you could delve in a little bit more regarding operational versus installed megawatts in the ground and what we should be focusing on with resource adequacy.
Thanks. That's a great question. And we had a lot of debate about that throughout this report. Where we ended up for this study is to focus on what we've called the physical resource adequacy challenge. And I think that's because we're primarily coming at it from the perspective of resource planners, where we need to know how much stuff should be in the ground to make sure that you can meet load. But operating a system as complex as the one that we're looking at will certainly lead to challenges that I guess there's sort of two solutions. You probably have to do both. One is to overbuild the system a little bit because you know you're going to make mistakes. And two is to really tighten up your operations and your forecasts. And to maybe be a little bit conservative during those, when you see a potential event coming, when we see weather that's potentially problematic, if you see a heat event coming that's going to affect a lot of major cities in the West, you probably want to turn everything on that you have. So there's some sort of easy fixes there, but then I think there are a lot more complex operational challenges that need to be tackled. Like I said, our storage and hydro and hybrid resources in this model are all operated optimally. So they see that there's excess renewables in some periods and they store all that up and they use it to avoid lost load in other periods. And we do need to make sure that we also adopt the operational innovations to make sure that we can actualize that in the West.
Right. Yeah. At some point, there's sort of like a crossover between planning and operations, and that the forecast stairs and how you plan for that storage use, given that there are going to be forecast stairs in the future, we may need to do some overbuilding to manage that.
Yeah. And with GridPath has the ability to do multi-stage commitment and dispatch.
Oh, excellent.
It's quite a bit more computationally intensive, and if you want to hear about that, I would invite Anna to chime in for this, because we tested so many conditions. We wanted to really strip it down and make it as fast as we could. But one of the kind of interesting things we found is it's really only a handful of conditions that cause big problems. For this system, it's something on the order of 100 weather days that were challenging on the system. And while, we ran 1,000 years of iterations through the simple model, and we needed it to be pretty fast so we could do that, you can make a model much more complex if you're zeroing in on the 100 most challenging days. And that's something we haven't tackled yet, but I hope people start to look at.
Sure, Anna, did you want to weigh in on that?
I was just going to add, yeah, once we sort of zero in potentially on the conditions, sort of adding that complexity as sort of a next step, like what is actually the effect of operational imperfections, and the fact that we can't like fully optimize the system the way we might see it in that ARIA analysis, it could certainly be like a next step in this once we sort of identify the first sort of physical adequacy type of problem and solve that. Can just layer that on.
Sure, excellent. The next question is, someone's curious if you could talk to imperfect capacity being able to avoid all of the shaded events. So they're going back to slide 9 and 10, where you had the shaded events that could be avoided, and wondering about storage or demand response or other kinds of imperfect capacity being able to avoid these shaded events. Like, are there consecutive events where storage just can't recharge in time? Or do you think storage or other imperfect capacity could avoid all of the shaded events?
So from this graph, you can't answer that question. This assumes that the energy is available when you need it. But from the simulation, you can look at how much excess, and I think Anna did that in the study to see sort of, well, would we have enough energy to charge up the storage if we were to add it?
Yeah, and we have sort of these weekly optimizations here, and certainly within that week, we know that we have the energy to actually address the events. We had a couple of these availability plots. We actually see that we have a good bit of extra potentially available energy. Certainly, at some point, we could. This is sort of a near-term system, a 2026 system, where maybe this is not quite as much of an issue yet. At some point, having enough of an optimization window, so that we can actually understand that, would certainly be potentially needed. But yeah, here I think because we have a dispatch optimization, we know that the energy is potentially available.
Okay, the next question is really related. It's basically saying their understanding is long duration storage is generally not needed then in the West to prevent reliability events, at least in what you've shown so far, assuming reasonable coordination among VAs is present. So assuming we can make all those imports actually happen.
Yes, and yeah, I think that if we're looking in the near term, long duration storage is not needed to achieve RA. But if we look in the long term, it probably will be. And I pull up this dispatch plot here because you can see very clearly how much we're relying on natural gas, the light gray area, to achieve RA during these days. And if we either retire that gas or we place a lot of limitations on how much it can run to achieve other objectives, then we're going to need something to fill that gap. This system is still very reliant on fossil fuel resources to achieve RA in the near term. So I don't think you should run with that we don't need long duration storage. It's just in the near term, with the system we've got, we don't need it yet.
Right, excellent. Next question is from Peter Mackin. He asked about the transmission model, and he asked if it was a power flow based model like DC power flow, or a transportation model that doesn't account for loop flow. And I think you talked about that, but maybe just reiterate.
Here we're using a transportation model with just simple losses. Once again, GridPath does have DC power flow functionality. We're just not utilizing it here.
Okay. The next question is asking about the public data resources for the development of the 2026 WEC model and for the perfect capacity additions.
Is the question, what public data did we rely on?
Right. What public data did you use for the development of the 2026 WEC model?
Yeah, we relied on the common case for the transmission topology, and then the load data was based on FERC 14, and then we developed our own sort of load forecasting methodologies for the case. Resource data was based on EIA, CAISO, BPA, all of the other acronyms. We've got thorough documentation of all the sources, and a lot of the sort of work that we did to take the historical data, you know, apply our approximations to estimate a future year, and then benchmark to the historical actuals where we could. That's all available. That will all be available in the report.
Great, thanks. So you made a really great case for getting more recent weather data. Someone is asking, how should we adjust historical record year data given climate change risks? What should we do to historical data given that we know the future is changing? That's a lot to ask.
Yeah, I mean, I personally, I think that we should use the historical data and be transparent about what we find when we use it. One of the challenges with Monte Carlo is you take all the historical data and you throw it all into a pot together, and then you pull out statistics, but you don't know where those statistics, you know, if you had more heavily weighted some of the recent years over the further away years, how would those statistics change? The nice thing about the weather synchronized simulation is that you can actually look at, okay, this weather year had this much risk, and that weather year had that much risk. And that allows you to just be more transparent about the amount of risk that you're planning for and how you're thinking about weather trends. To me, it seems like we've got to move in the direction of sort of climate simulation informed weather data sets for these, but also recognize that that could be a massive undertaking. Given all of the uncertainty and the scenarios that we want to look at and how high resolution, I mean, these data sets are hourly over several years across hundreds or more sites across the footprint. That's a ton of data to be looking out across all the climate scenarios as well. So it's a big challenge. And what we tried to provide here was maybe one way we might think about sort of shortcutting a little bit of that by using these statistical models instead.
Excellent. Yeah, it's definitely a huge challenge, and we've got an extreme weather task force trying to look into this as well. We're really hoping to get some recommendations out there on maybe someone could create some new data sets. Okay, the next question is asking, is your study based on existing transmission, or does it assume perfect transmission or something else?
It's based on the transmission in the 2026 common case. We did not look at transmission outages in the final simulations. We did a few key sensitivities as we were doing the study where we like took out the COI, and that was during a particular wildfire event. We thought, oh, what happens if, you know, so in the end, we found that things weren't all that sensitive to specific transmission outages because there's so much redundancy in the high voltage transmission system. But you could certainly layer in transmission outages if that's something of interest in the future. There's sort of the infrastructure in place to do that.
Right. See, someone's asking about the report, which you said is going to be out shortly, and you've got the link at the end of your presentation and that presentation is going to go out to everyone. So they'll be able to access it when the report is done. Another person asked, the RAP area analysis is interesting because of the presence of hydro. Does that limit the ability of batteries to provide that flexible capacity?
It's certainly, I guess you're further along the declining marginal value curve for storage when you've got a system that has a lot of hydro. But we did find when we took the coal out and zeroed in on the RAP footprint, we still saw these pretty short duration, sort of 2-hour problems that could be well suited to batteries because you might just be in a circumstance where you've maxed out your hydro in those situations. This is an August problem, and our hydro is constrained based on the historical sort of fleet-wide operations of hydro during the different hydro years that we test. And so I think in those events, you still need a little bit of capacity.
Okay, great, thanks. Okay, I'm realizing that we're at the top of the hour, so we're gonna need to wrap this up. I really would love to thank you guys, Elaine and Anna, for a very informative presentation. Great work on developing this new toolkit. I hope all the participants found something useful to take home. And we'll send out an email once the video file's posted. We'll answer the questions we didn't get to and get them posted as well. And we appreciate everyone's participation. Look forward to seeing you again, maybe at the fall workshop, which starts October 24th in Minneapolis, or the next webinar, which is the combined GPST ESIG webinar on probabilistic resource adequacy methods that Derek Stenslick of Kalos Energy will present on. And you can get more information at esig.energy. Thank you again, Elaine, Anna, for a very timely, very informative webinar. We look forward to seeing you again in the near future. And in the meantime, everyone take care and stay safe, and thanks for your participation. Bye.
Thank you, everyone.
Thank you.